time of the day, dear colleagues. I'm happy again to greet you at Moscow Engineering Physics Institute of National Research Nuclear University of Russian Federation, and we are considering examples from the admission tests to our university. This time we will consider a couple of examples, couple of exercises from electrostatics. To find the results, to find the answers for the questions that will be addressed to you in these examples, you will need to know not so much. You will need only to know some definitions. Definition how to calculate electric potential, for example. Let us consider the first exercise. Imagine that you have two charges, point charges. One positive, well, Q, and another one negative, minus 4Q. The negative charge is much higher than positive by absolute value, but negative. So the positive charge generates positive potential. Negative charge generates negative potential. Somewhere in between, there should be a point with zero potential. The question is, at which distance x from the first positive charge this point is located? To find the solution, you need only to know the definition how to calculate potential. Potential of any charge, if the charge is located in a point, well, depends on the value of the charge, the distance from the charge, and that's all. Potential is equal to the ratio of the charge, the distance from the charge, r, and some constant, which is called the Coulomb law constant. So, in our particular case, we have two charges, positive and negative. Let's consider a point at the line between the charges, which is located the point at the distance x from the positive charge. Then the potential generated by the positive charge exactly at this point will be looking like that. K, Q capital divided by x. And the potential generated by the negative charge at the same point, this is important, will look like that, minus, because charge is negative, 4, because charge is 4 times higher in value than the positive one, and L minus x is exactly the distance between the negative charge and the point, which is x centimeters away from the positive one, because the distance between two charges equals to L. So, practically, we have found already the result. Potential will be zero, where the two terms in this equation do compensate each other. It will happen exactly at the point which is located at the distance x equal to the distance between charges A divided by I. Another example is a little bit more complicated. Again, we have some charges, but in this case, those charges are little conducting balls, liquid balls, drops of conducting liquid, something like mercury. You see that, well, if all these charges are little, we may consider them as if one charge. If all these charges are conducting, so we may charge them somehow. So all of them are charged to one and the same charge, and all of them have the one and the same potential. The surface of the ball and everything that is inside, where the ball is conducting, have the same potential. You should know. So the potential of the little ball, liquid ball, of a little drop, is equal to 1 volt, each of them, and in total we have 64 such little conducting drops. This is the condition of, this is simply just what we have in the condition of the exercise. The question is, if now all these drops will merge into one big ball, what will be the potential of this ball? Again, we should use just only the definition how to calculate the potential. Potential of a drop with radius r will be equal to the ratio of its charge and this radius multiplied by the Coulomb law constant. So now we should apply also some knowledge from geometry and some common sense. After I will have After I will merge all the drops together into one big ball. This big ball will have the volume equal, it's simply pure common sense, to sum of volumes of all little balls. So the volume will be 64 times higher than the volume of each little drop. Now the question is, what will be the charge of it? The charge of it will be equal to 64 charges of little drops, because the charge cannot disappear. It is conserved. It is conserved, and this is valid absolutely. The law, the charge conservation law, is absolutely valid as the energy conservation. So charge is conserved, 64 little q's is the charge for a big ball. Now what will be the radius of the big ball? It will be equal to 64 radiuses of little ones? No. The volume will be equal to 64 volumes of little ones. But from geometry we do know that volume is proportional to the radius cubed. What factor shall I cube in order to obtain 64? Think a little bit. It's 4. 4 multiplied by 4 is 16, multiplied again by 4 will give you exactly 64. So the ball in which all 64 little drops will merge will have the radius 4 times bigger than the radius of each little drop. So we may now calculate the potential. K is the same, the constant. Q capital is 64 Q littles, and R capital, the radius of the ball, is 4R littles. Result is 16 littles. That's all for this section. See you in the next episode. We will consider another field of physics. Bye.